Jai Shri Gurudev. Dear students, welcome to session 2 of module 3. In today's session, we shall discuss about the second topic of time response analysis of feedback control systems. So in the last session, we have discussed about standard test signals and we have learned how to find out the impulse response of a first order systems. So we shall continue with the next topic in today's session. So in today's session, we'll try to find out the unit step response of the first order system. So I've explained you what is an first order system and what are the standard signals that is used to analyze the system. And in today's session, we'll try to analyze the first order system using the unit step signal and we'll try to find out the unit step response for this system. So considering the block diagram of a first order system, so this is a general block diagram what we have for the system with the transfer function as k divided by ts plus 1, where k is the DC gain and t is the time constant. Now for this I am giving an unit step signal as an input. So u of t is your unit step signal. The Laplace transform of your unit step signal is given as u of s is equal to 1 by s. Now this is taken as our input r of s. Now we are supposed to find out the value c of s for this particular input. Now c of s, as you know, it is taken as k divided by ts plus 1. So transfer function is usually it is represented as t of s by c of s by r of s. If I cross multiply this r of s here, so you will be multiplying this by 1 by s. That becomes the transfer function for your system. So c of s for this particular unit step signal is taken as k divided by s into ts plus 1. Now we will try to find the inverse Laplace transform for the equation for c of s. So we need to break this using the partial fraction expansion and then we are supposed to separate the terms and then we will be applying the inverse Laplace transform. So partial fraction expansion knowledge you must know for this. So we'll see how this happens. So here we will be separating the terms using the two partial fraction terms, and when you find out the value of a and b using the partial fraction expansion, you can simplify c of s as equal to k divided by s minus kt by ts plus 1. So this is the value of your output you have got in the Laplace transform domain, for which you have to apply the inverse Laplace transform. Now this is called, the first one is called as your forced response and the second one is called as the natural response of the system in this particular example. So the total response is nothing but summation of the forced response and natural response. So we are taking this c of s, so k is taken as constant, so k into 1 by s minus t divided by ts plus 1. So by taking inverse Laplace for this particular term, you know that inverse Laplace transform of 1 by s is nothing but equal to u of t, and inverse Laplace transform of your constant divided by ts plus 1 is nothing but an exponential signal which you will be getting as e to the power minus t by t. So this is the output response what we have got as a step response for the system by taking input as u of t. So if u of t is taken as a unit step input, then you can get c of t as equal to k into 1 minus e power minus t by t. This is the unit step response, or normally called as the step response for the first order system. And when t becomes equal to t, that is when your time constant t arrives at the fundamental time period t, c of t is taken as k into 1 minus e power minus 1, which is nothing but equal to 0.632 k. This is the c of t value when t is equal to capital T. Now this is the pictorial representation of the response what we have got by taking an example as k equal to 10 and t equal to 1.5 seconds. So if I replace these two values, I'll be getting an exponential response like this. Okay, so your DC gain is taken as steady state output by input, so it is 10. And this is the input what we had given for the system, and this is the response of the system what we have got for the first order system with input as unit step. And here I am taking a few more examples for my t. So t is taken as 1, 3, 5 and 7. K is taken as 10. So for t equal to 1, your response is like that. Here it is indicated in blue color. For t equal to 3, this is the response which is highlighted in green color. And for t equal to 5, this is the type of the exponential response which we have got, which is highlighted in red color. And for t equal to 7 seconds, this is the response which is indicated in sky blue color. So you can see there is a variation in the response depending upon the value of t, even though DC gain is constant. So system takes 5 times constant to reach its final value. From the previous observation you can see when t for t, 2t, 3t, 4t and 5t, your response accuracy of your response is getting increased and your system is able to reach the steady state at this particular point almost. Okay, so slope here is taken as equal to 1 by t. So your system is taking 5 time constant, that is 5t, to reach the steady state response for this particular example. And similarly, I'm varying my DC gain now, and t is kept as constant. In the previous response, if you can see, k was kept constant and time constant t was getting varied. Now you can observe we have got 4 different types of response for 4 different values of k. So for k equal to 1, this is the response what we have got in blue color. For k equal to 3, you have got a response which is indicated in green color. For k equal to 5, we have got a response which is shown in red color, and for k equal to 10, you can see this is the type of the response what we have got for c of t equal to k into 1 minus e power minus t by t. From this, what we can finalize is the step response of first order system is given as k into 1 minus e power minus t by t. So by differentiating c of t with respect to t, we can get the value of dc of t by dt as k by t into e power minus t by t, which is nothing but the impulse response of the system. So derivative of the step response of the system is nothing but the impulse response of the system. This is the relationship we have learned. And integral of your step response will give you the integral of your impulse response will give you the step response, and vice versa. This is one important relationship what you must know. Now let's take one example and we'll try to find out the time constant value t, DC gain, transfer function and step response for the c of t value, which is given as 3 into e power minus 0.5 t. The first thing is the Laplace transform of impulse response of the system is nothing but the actual transfer function of the system. So first we'll take the Laplace transform for this particular example by taking the input to be an unit impulse input. So C of S is nothing but equal to 3 divided by S plus 0.5, right? So this is our C of S by delta of S or C of S by R of S. I'm finding the impulse response first. Okay, so which is in turn can be represented as 6 divided by 2s plus 1 in the time constant format. So here you can see C of S is nothing but equal to what? 6 divided by 2s plus 1. So this is nothing but our k and this becomes our t. So I have got time constant as 2 and k as equal to 6 and transfer function is equal to 6 divided by 2s plus 1. Now the next step is you need to find out the step response. That means you have to take R of S as equal to U of S and then you have to find out the step response and draw the step response for the system. Now C of t, you know, so I am taking the integral of C of t, which is giving me the value as equal to this. So you can find out C using the initial condition of C of S as equal to 0. So C you have got it as equal to 6 and C of t is 6 minus 6 into e power minus 0.5 t. This is one way. Or else another way of finding the step response is you can take R of S as equal to 1 by S, cross multiply, and then take the partial fraction expansion like this for the given term. Find out A, B values. So you'll get A value as 6 and B value as 6. So it is taken as 6 divided by S into 2S plus 1, which is equal to 6 by S minus 6 by S plus 0.5. And then take the inverse Laplace transform. So C of t is nothing but equal to 6 minus 6 e to the power minus 0.5t. So two procedures are there. Whichever is feasible for you, you can follow. Either take integration or use partial fraction expansion like this. So this is considered to be the most simpler way. So try to follow this procedure only, second procedure using partial fraction expansion. And now we are trying to find the ramp response for a first order system by taking R of S as equal to 1 by S square. So C of S is taken as equal to what? If R of S is equal to 1 by S square, so it is K divided by S square Ts plus 1. The ramp response after taking inverse Laplace transform, you are going to get it as equal to C of t equal to K into t minus t plus t e power minus t by t. And if you try to plot the ramp response for a first order system, it looks like this. Okay, this is the response what we have got, which is indicated in green color. Okay, a sort of exponential signal which is similar to your linear ramp signal. So this much is the error which is shown, and when k equal to 1 and t equal to 3, this is the response what we have got, and you can see the error rate has increased when you increase your delay 3. So therefore t should be less to have less error in case of response using the ramp signal. So we are considering now an example of a parabolic signal. So this is the transfer function what we are going to get for a parabolic signal with output response as C of S is equal to K divided by S cube into Ts plus 1. Same procedure you have to follow and try to solve it. Okay. Now coming to practical determination of the transfer function of a first order system, it is not possible to practically determine the system transfer function. We always use the analytical procedures. So here if we can identify t and k, and we can obtain the transfer function for a first order system practically. Okay, so let's assume an unit step response as shown in the figure. Okay, so from the response we can measure the time constant, that is time for the amplitude to reach 63%. Okay, here almost steady state, this part, that is 63%. Okay, since the final value is about it is reaching the steady state around 0.72, the time constant is evaluated where the curve reaches 0.63 into 0.02, that is 0.45. So about 0.13 seconds is taken to reach the steady state in this case. Okay, so this is the value that is taken to find the, this is the final value that is taken to find the response. So k is simply the steady state value, which is nothing but equal to 0.72, where your response is almost reaching the steady state. Thus the transfer function could be taken as k is 0.72, t is 0.13 s plus 1. Or after simplification you can take it as 5.5 divided by s plus 7.7 also. So let's take a first order system. In the previous thing there was no 0. Here we are taking a 0 which lies at minus 1 by alpha and a pole at minus 1 by t. So for step response of this particular system is determined by taking R of S as equal to U of S, and this is the value what we are going to get after partial fraction expansion, and we are getting the C of t value as k plus k by t into alpha minus t power minus t by t, right? So this is, the first one is nothing but response without 0, that is with only one pole, and this is the response with 0. So if t is greater than alpha, the response will be the same almost. Okay. Now this is the response what we have got for the um, first order system with 0 unit step response by taking k and t values. So this is with t less than alpha. This is a decaying response what we have got for the system with 0. So those two responses are combined and it is totally shown in this figure. So this is the response of the system with 0 and without 0, which is shown here in blue color, green color and red color. Red color 1 is the response of the system without 0, and blue and green color is the response of the system with 0 when t is less than alpha and when t is greater than alpha. So this is one example which you can try. So try to find out the impulse, ramp and parabolic response for the system with 0. So these are few examples. So if I take a thermometer which requires 1 minute to indicate 98% of the response of the step input, assuming the thermometer to be a first order system, find the time constant. So this is what is given to us, a practical example. So second thing is, if a thermometer is placed in a bath, the temperature of which is changing linearly at a rate of 10 degree per minute, how much error does the thermometer show? So try this also. This is one of the practical example which correlates with the first order system response. Now coming to pole zero map and step response. So for k equal to 10 and t equal to 1, I have a pole at s equal to -1, which is shown here with the red color. Now it's another example where I'm taking C of s by R of s is equal to 10 by s plus 2. In such case, when you simplify this in the standard form, you can observe here that you have a pole at s equal to -2, which is shown here, and t equal to 0.5 seconds. So few more examples are shown in the similar way. So we have s plus 3 here. So I have a pole here with the time constant as 0.33 seconds after simplification. So this is the comparison of the step response for the two examples. So if you can observe here which one is reaching the steady state early, the second one is reaching the steady state early. So let's consider the systems with delay and without delay. So if I include a delay time TD for the response, let's see what happens. So your unit step response for the system with delay comes like this. So it is, instead of getting a response like this, you have a slight variation in the response if you include a delay. Okay, this is with example. So few examples of your first order system, if we can quote, armature control DC motor with LEA equal to 0 could be considered as an example of a first order system, because your S value here, power of S is 1. So degree of the transfer function is 1. So this is considered as an example of a first order system. And similarly, in an electrical system, an RC circuit network like this could be taken as an example of a first order system. It is looking similar to that, right? So K divided by Ts plus 1, where this is RC is taken as your time constant. K is taken as 1 in this case. And this is an example of a mechanical system with the spring and a dashpot. So which is given as 1 divided by Bk plus S plus 1. So this is taken as your T and this is taken as your K. Time constant here is B by K. So I hope you have followed the concept what I've explained in today's session. So in today's session, we have discussed about unit step response of the first order system, and you have learned how to find out the step response for the system, and we have derived the expression for that, and we have taken the inverse Laplace transform for the response, and you are able to observe the type of the response what we are going to get for the system by variation of the gain and time constant. Few examples we have quoted for the first order system also. And these are my reference books from which all these concepts are taken. So a few more examples you can take from the same books and you can solve. Thank you all. Have a nice day. Jai Shri Gurudev.